Hello, everyone. Great pleasure to be here today to talk to you about models, metrics, tasks, as well as fairness in vision and language. Lots to do in a short period of time, so let's dive right on it. I'm Olga Russakovsky. I run the Princeton Visual AI Lab. This is us. In particular, I want to point out Dora, Zayu, Jiwei, and Arjun, who you'll get to meet a little bit later in the talk. So our research is on computer vision, specifically looking at visual recognition and reasoning. So trying to build systems that can look at an image or a video and make sense of everything that's going on in there. We've worked on a number of perception tasks, so things like image classification, object detection, spatial relationship recognition, action or activity recognition, and video. In some of these, so for example, for the object detection or the action recognition work, we've really focused on the modeling part, so trying to build a better deep learning system that for this task. For others, like the spatial relation recognition work, we've realized that the bottleneck is not quite on the modeling side, but actually on the benchmarking. And so instead of thinking about the next cool model, we've developed a framework for collecting better data and then released a better benchmark for this task. So progress in computer vision can take on many different paths. So if we think about the computer vision system more generally, right, so there's some training data, there's an algorithm, there's some test data. A lot of the focus is frequently on the algorithmic side, on the building a better model. But of course, there's a lot more than that. And so arguably, when we think about perception, that's sort of one piece of the puzzle. In order to develop and deploy these systems actually in practical real world setting, there's also the interaction piece. There's the question of how do we design systems that can best learn from or collaborate with people? So in this diagram, right, we would think about people who are providing training data, for example. So how do you get the best possible labels in, given a short amount of time from a short amount of human time? Can think about, you've deployed this computer vision system in the real world, whether it's on an embodied agent or in some kind of application and like image search, like medical diagnosis, right? So the question is it going to be able to do this task entirely on its own, which is sometimes true, or would it be more effective if it's doing this task in collaboration with people, so people are able to kind of provide feedback, the model is able to continually learn from people. And one of the critical pieces in this collaboration, of course, is language. So people communicate in natural language, and so designing computer vision systems that are able to make use of that and use that as a mode of communication with people are going to be much needed and very effective in practice. So a lot of the talk will focus on this language component today. There's one more sort of key challenge I wanted to highlight, right? So there's perception and interaction, and the third piece is fairness. So in fairness, we realize that these computer vision systems are affecting everybody, and we ask who is represented, right? So who's represented in the training data, who is represented in the models, who's represented among the decision makers who are making critical decisions about what kind of systems to build, what kind of data to collect, sort of how to go about this process. So when we think about perception, interaction, and fairness in the lab, these kind of a lot of the projects sort of fall at the intersection of some of these challenges. And so here today we'll talk about vision and language, which arguably falls at the kind of at the intersection of perception and interaction, right? So this is vision and language work. We'll talk about three particular projects first. So we'll do sort of short spotlights on each of them. So one will focus on modeling. So Jiwei Deng will introduce a new model that we've developed for the task of vision and language navigation. The second piece, we'll talk about metrics. So Zayu Wang will talk briefly about a new metric that we've developed for image captioning. And in the third piece, we'll talk about tasks. So Arjun Mani will give a brief introduction to pointing VQA, which we've developed as an extension of standard VQA. So with that, I will pass it off to Jiwei, Zayu, and Arjun. And then when we come back, we'll talk about fairness.
Hi, everyone. This is Jiwei Deng. and I'll talk about our paper on Evolving Graphical Planner, published in NeurIPS 2020. This is a joint work with Professor Karthik Narasimhan and Professor Olga Russakovsky. Our paper tackles the problem of vision and language navigation. We're given a text-based instruction and an environment. A robot needs to follow the instruction and navigate on the correct path to reach the target location. We propose a differentiable graphical planner that performs planning for the robot. Specifically, instead of only locally decides where to go next, our model keeps a graphical memory that stores the raw features of each node and make decisions over a global action space. Our planner uses a condensed graph for efficient planning and utilize the graph structure to generate supervisions to reduce the mismatch issue in VLN. We found that our model performs well on two standard benchmarks, room-to-room and room-for-room. For example, we can achieve CVPR performance on room-for-room through pure imitation learning without relying on reinforcement learning fine-tuning. You're welcome to check our paper for more details.
Next, I will talk about a new metric we designed for image captioning. I would like to mention two other collaborators. They are Bertie Feng and Professor Karthik Narasimhan. Despite being reasonably accurate, modern image captioning models produce generic captions, leaving out important details. In this work, we first quantitatively demonstrate limitations of current captioning systems and metrics, showing that models often prefer common, even incorrect sentences over descriptive but less common ground truth captions. And current metrics like spice, without notion of uniqueness, can be fooled by a simple object detection model. As a step towards addressing the issue, we propose a new metric called SpiceU, which is defined as a harmonic mean between spice score and the proposed uniqueness score, specifically designed to capture descriptiveness of captions. And through experiments, we show that SpiceU is better correlated with human judgments compared to existing metrics. Finally, we also propose an inference time re-ranking technique as a simple complement to existing captioning models, and show that the generated captions have higher SpiceU score and qualitatively more descriptive with less hallucination of common objects. We hope the proposed SpiceU metric and other findings in this work would help on building better captioning systems.
Hi everyone, my name is Arjun Mani, and I'll talk about a new task we introduced incorporating pointing into visual question answering with Nobleen Yu, Will Hinthorn, and Olga Russakovsky. Pointing is integral to human communication in the visual world, and real-world AI systems should understand pointing as part of a dialogue. Our contribution is to extend VQA to questions involving a point input. We contrast this novel task with prior work, introduce 3 challenging settings and benchmark datasets within this task, and propose model designs to answer point input questions. Pointing has been used in computer vision as a form of supervision for tasks like semantic segmentation or in the pointing game used for evaluating spatial attention. In our work, we use pointing as input at training and test time for VQA. For example, designing models which can answer questions like, what color is this shirt? Prior VQA tasks containing spatial reference include which questions in Visual 7W with bounding boxes as candidate answers, or in Visual Genome with questions associated with particular regions. We differ in 2 respects. First, we use the more natural point rather than a bounding box for reference, which challenges the model to infer the extent of the object pointed to. Second, we constructed our benchmark so that a point is necessary for answering the question. For example, here without a point, the answer to the question could be black or white. We introduced 3 benchmarks for pointing VQA. The input is always an image, question, and XY coordinate of a point. In point QA local, we have questions like, what color is this shoe, which can be answered by looking at a local region around the point. In point QA look twice, we examine counting questions like how many of these objects are there, which require the entire image context. Finally, in point QA general, we examine unconstrained, human-written questions that require reasoning about image, text, and point in full generality. We verify that the point input is in fact necessary, since a model that sees only the image in question, but not the point, obtains a random chance of 50% on point QA general. We expand existing VQA models to successfully incorporate the point input, reaching relatively high accuracies, although still significantly below human performance. Please check out our paper at the link here.
So thanks very much, Ziyu and Arjun. So we've talked very briefly about some of the models, metrics, and tasks that we're developing. And now let's turn our attention to fairness. So let's talk about what kind of fairness issues might arise in computer vision systems, as well as specifically in vision and language models, and how can we go about mitigating bias in these systems. So let's start with a high-level overview of the fairness questions. So over the past 5 years or so, there's been increased attention both in among the public, among the media, as well as in the scientific community around questions of machine learning fairness. So there's been news headlines like computer vision model learns to quote unquote increase attractiveness by manipulating skin color. Machines taught by photos learn a sexist view of women. Facial recognition is accurate if you're a white guy. This was the seminal work of Joy Buolamwini and Timid Gebru on face recognition. And there's been a number of books that have come out, like Algorithms of Oppression by Safiya Noble, Race After Technology by Ruha Benjamin, taking a very deep dive into sort of the root causes of bias in technology, as well as really analyzing the downstream impact. And these are absolutely excellent books, highly recommended if you're sort of interested in this space. For the purposes of this talk, though, and for our work, we're actually going to simplify this to a pretty simple cycle, right? So we know that there is human history biases and prejudices that are making their way into our large-scale data that we're collecting. We're training AI models on this data, and the AI models are then making decisions, which become part of our history. And so the question that we ask is, can we offer constructive computer vision and machine learning solutions to try to mitigate the effects of this cycle? Or in other words, right, so we have engineering expertise, we know how to build these systems. And so the question is, can we think about engineering solutions to some of these effects and think about, what can we do in practice to do better, more responsible, more inclusive, more representative, less biased computer vision design? One thing I want to particularly highlight here is that you might think that these fairness issues only arise when we're talking about data of people. So when we're talking about face recognition or activity recognition, but there's been a number of works that demonstrate that fairness issues are actually pervasive, even in something like object detection, which you might think, object recognition, why would it have any kind of fairness issues? So it turns out that a lot of modern computer vision data sets are actually very geographically homogeneous. So they come from particular countries and are missing out entire parts of the world, which means that when you build object recognition technology off of these data sets, what ends up happening is that the object recognition models can work in some countries, but not others. And one particular example is you're building an object recognition system that can recognize common household objects like soap. And what the model is going to learn is to recognize US brands of liquid soap, because that's what's represented in the data. And this, of course, becomes a problem when you try to deploy this at scale and you realize that it's failing gloriously on bar soap, which is what's used in the vast majority of the world because it's underrepresented in the data. So let's take a deeper dive into fairness, specifically in the visual language space, where Dora Zhao will talk a little bit about our latest work in examining bias, specifically in image captioning. She will talk about different demographics of people. This will be more of a people-focused project, but I did want to flag the geographic diversity as well, just to make it clear that this is a question that's very, very relevant across all parts of computer vision.
Hello, everyone. My name is Dora Zhao, and I will be presenting our paper, Understanding and Evaluating Racial Biases in Image Captioning with Angelina Wang and Olga Russakovsky. So in our work, we make two main contributions. First, we collect demographic annotations on the Common Objects in Context, or COCO dataset. And then using these annotations, we then assess the pathways for bias propagation within image captioning systems, looking at the ground truth images, manual captions, and automatically generated captions. And so while racial biases have been uncovered in many computer vision tasks, including gender classification, pedestrian detection, and image tagging, we turn our attention to the task of image captioning. So image captioning is particularly interesting, not only because it involves both a visual and a language component, but also because of the important societal applications of image captioning for accessibility. And one question that arises with regards to race in this context is whether racial descriptors ought to be included in the generated image captions or not. And so on one hand, in some contexts, individuals who are blind or low vision may want to have racial descriptors, and further that they ought to have the same information that sighted individuals have. However, on the flip side, there's always the ethical implications of assuming the race of individuals. And in our work, we consider not only the use of racial descriptors and automated captions, but also other ways in which racial biases can propagate in image captioning systems. And so for our bias analysis, we begin by crowdsourcing skin color and perceived gender expression annotations for COCO. In total, we collect annotations on 15,762 images from the COCO 2014 validation set. And consistent with prior works, we find there's an underrepresentation of individuals with darker skin tones, and note the unique intersectional underrepresentation faced by darker skinned females. And beyond being used for this work, we have released the annotations for future research. And so using the annotations we collect on the COCO dataset, we assess the pathways for bias propagation within image captioning systems. We start by looking at the ground truth images and manual captions from COCO. For the images, we find that there are differences in visual appearances, such as in the simple image statistics and the object co-occurrences. Next, we consider the manual captions. We note the presence of slurs as well as the use of racial descriptors. And now finally, we consider automatic captions produced by image captioning models, including looking at the use of racial descriptors and differences in the caption accuracies. We also analyze the differences in caption content. However, since we found differences in visual appearances, we need to first disentangle the differences that come from the image content versus the captions themselves. And so to do this, we find pairs of images that have similar visual appearances differing only by the skin color of the individual. And in total, we use an evaluation set of 876 images for this purpose. And using these images, we are then able to examine where and how captions diverge, even when the visual differences are controlled for. And so we find that both manual and automated captions differ depending on the skin tone of the individuals pictured. And we train a classifier to see whether or not it could differentiate between captions describing lighter versus darker images. And so first, to see whether the semantic content differs, we train a multi-layer perceptron on the sentence embeddings. And we find that there is that the manual captions are differentiable. And so this suggests that there's a learnable difference in the way human annotators are describing different skin tone groups, even when the visual appearances are indistinguishable. However, we do know that this ability to distinguish between lighter and darker decreases for the automated captions. And so next, we look at the differences in the vocabulary used. And unlike for the sentence embeddings, we find that this ability to distinguish actually increases for the automated captions. And moreover, we note that there is an increase in AUC from the older models, such as FC, Add-to-It, or DISCAP, to the newer transformer-based models. And so this indicates that bias may be increasing for newer models. And so overall, our work provides a foundation for assessing how racial biases propagate in captioning systems and also uncovers existing biases. Nonetheless, it is likely that as the image captioning space continues to progress, the biases present will increase as well. And thus, this precipitates the need for future work that aims not only to further analyze, but also to mitigate these biases.
So thanks very much, Dora. So just to conclude this discussion of fairness, it'd be amiss if we didn't talk a little bit about representation and the bias that comes from having a very homogeneous group of decision makers within AI. So if we're trying to build fair computer vision systems that are inclusive and that are representative, one of the things that's going to be critical in this path is making sure that we have all voices represented at the table when deciding what applications to tackle with computer vision systems, where to collect the data, what kind of critical questions to ask about this technology. And so let me talk to you just very briefly conclude here by talking about AI for All. So AI for All is a nonprofit that I co-founded a few years ago together with Fei-Fei Li, who hopefully you've all heard about, as well as Rick Summer, who's an expert in K-12 education. AI for All is a nonprofit dedicated to increasing diversity and inclusion in AI. We like to say that AI will change the world. It's already changing the world. And the question is, who will change AI? And so our goal is to educate and support a diverse next generation of AI leaders, specifically with emphasis on the word leaders. We are trying to find students who are currently in high school or early college or middle school, primarily focusing on high school, who come from groups that are traditionally underserved and underrepresented in AI, and provide a pathway for them towards becoming leaders and key decision makers in AI. So we provide educational programs, ongoing mentorship, ongoing community and ongoing opportunities for as long as they choose to stay in AI, because we believe it is very important for the field as a whole to have this diversity of voices and diversity of thought in the next generation of AI leaders. And one of my favorite quotes from AI for All is a student who said in 2016, "Until this program, I never thought that people who look like me could succeed in computer science and AI. And this is why we do what we do." So this concludes the talks talking about perception, interaction, and fairness, specifically our work on vision and language. I'd like to give a big shout out to Jiwei, Zayu, Arjun, and Dora. So Jiwei is finishing up his postdoc. He is looking currently for opportunities as a research scientist. Zayu will be graduating with his PhD next year. Also will be looking for opportunities as a research scientist. Arjun is starting his PhD at Columbia next year. We'll probably be looking for internship opportunities over the next few summers. And Dora is applying to PhD programs in the fall. So if you're looking for PhD students, definitely be on the lookout. But I also thank all of the rest of the students in the Visual AI Lab. And please visit us, visualai.princeton.edu, as well as aiforall.org to learn more about AI for All. Thank you.